Now that Griselda has taught us a little bit about the theory, let's dive into the assumptions.
A quick disclaimer. The model that we created was for demonstration purposes only. Not all of our assumptions will be met, but we want to give you the code so that you can check future assumptions of future models.
Here we go. In this video, I will brief all of you on the assumptions of multiple linear regression with interaction while simultaneously demonstrating on how to check them using R. Let's get started with the assumptions. The assumptions are as follows. First, linearity. Here, we check for a linear relationship of the outcome variable and the independent variable. As for our data set, our independent variable x is MPG. Second, autocorrelation. This assumption checks for the independence of the error terms. Third, homoscedasticity, also known as the test of equal variances. And lastly, multivariate normality, that checks for the normality of the error terms. Let's start with linearity. To check if the model is appropriate for the data being analyzed, we want to see a linear relationship between the outcome variable and the independent variable. There are three separate ways we can do this. The first is to plot a scatter plot. The second is to plot the values of the observed versus the predicted. And the third is to plot the values of the residual versus predicted. Now, before I get into this, I will now attach our data set, that is subset cars. And then I will run a scatter plot. Now, by looking at a scatter plot of the data, we should be able to see if there appears to be a linear relationship between the data. And let's see if that works. Here. You can clearly see that there is a missing linear relationship since there's an evident curvy linear relationship of the data points. We have two fit lines here. The blue one represents the line for 4 cylinders and the magenta represents the line for 8 cylinders. Going forward, I will now run the two plots. Let's look into this. Now, for this plot, we want the observed values and the predicted values close to each other, which is evident that they are not. That also tells us that there is a missing linear relationship. Now, coming to this plot, the observation should be near the line here and it should be without a clear pattern. But as you can see, they are not near the line. And also, from our plot, we can see a curvy linear regression function. The residual values tend to vary in a pattern between the positive and the negative, which also indicates a missing linear relationship. Now that we have non-linearity in our data set, a few remedies that we could do is to run a quadratic linear regression function or a nonlinear exponential regression function. This transformation approach employs a transformation to linearize a dataset at least approximately. Let's move on to autocorrelation, also known as the independence of the error terms. There are two ways in which we can check for this assumption. The first way is by running a statistical test known as the Durbin statistic, and the second way is to visualize a plot known as the autocorrelation plot. Let's start with the statistical test. Now, the Durbin-Watson statistic indicates whether there is autocorrelation and the degree at which it is present. Autocorrelation ranges between 0 and 4. The values that are less than 2 indicate positive autocorrelation, and the values greater than 2 indicate negative autocorrelation. Let's keep in mind here that the null hypothesis is that the true autocorrelation is equal to 0, and the alternative hypothesis is that the true autocorrelation is greater than 0. Now, before you run the Durbin-Watson test, keep in mind that you have to install the package car. Since I've done that, I'm going to run these lines of codes, which will give us the test. As you can see that our p-value is 0, that it is less than 0.05, which means that we have to reject our null hypothesis, which means there is a definite pattern in the residuals. Now let's plot the autocorrelation plot. And For the residuals to be not autocorrelated, the correlation y-axis will drop to a near zero below the blue dashed line right here, which represents the significance level. As you can see from our autocorrelation plot, the correlation values drop below the dashes over here, these values here, which conclude that the autocorrelation doesn't exist and the assumption is not met. Now, a way to rectify this would be that you can add one or more predictor variables. Now, only when the additional predictor variables is not helpful, transformation of variables can be employed. Let's talk about homoscedasticity. This assumption is concerned with the variation of the residual, or as we call it, the amount of error in the model. It states that the variance of the error term is analogous for each independent variable across the model. Alternatively, if the variances are not equal for the independent variables across the model, this would indicate a condition defined as heteroscedasticity. If the data displays heteroscedasticity, it would mean that we have overestimated the goodness of fit, which basically tells us how consistent our variables are. The advantage of this particular assumption is that you can easily and very clearly point out if there is a breach, which helps us define the accuracy or the precision of the model. Now, the null hypothesis for this assumption is that the variances are equal, and the alternative hypothesis is that some of the variances are equal. The following are the ways we can examine homoscedasticity. Let's start with the first one, where we use a statistical test known as the Breuer-Spagan test. It is a chi-square test, and the test statistic for this test is distributed with k degrees of freedom. Now, in R, this test is executed by the function and CV test that is available in the car package right here. For homoscedasticity to be present, the chi-square value has to be low and the p-value has to be less than 0.05. Let me run this test for you. As you can see from the results of the NCV test, it gives us a very high chi-square value, that is 80.89, and the p-value is approximately 0. Now, moving forward, the second statistical test that we will be using is the BF test. Now, to conduct this test, we have to divide the data into two groups, where one group consists of cases where the level of the predictor variable is relatively low, and the other group consists of cases where the level of the predictor variable is relatively high. So, you first have to install the package one-way test, and I will now first subset the cylinders here, and now I'm going to run this test for you. Now, as you can see that our p-value is less than 0.05, this means that the variances are not equal. An important point that I would like to add is that the more interactions or subgroups of the data, we can say that the SDs or the standard deviations or the variances are not same, since each of the groups comes with its own standard deviation or variation. Concluding from all this, we can say that the assumption of homoscedasticity is clearly not met and follows heteroscedasticity. Now, when we have a non-constancy in our model, the one way to modify the model is to use weighted least squares method to obtain the estimators of the parameters. Also, transformations like Box-Cox transformation help the model precisely, and we could then get an assumption of homoscedasticity. And lastly, let's talk about multivariate normality. We want to see if the residuals are normally distributed. We can check for normality by visualizing a QQ norm plot. Here, the points should lie close to the line to be considered normally distributed. They should not appear to be skewed. Now, I'm going to plot this plot for you by running this line of code. And as you can see from our plot that some of the points lie far away from the line, which means that there are some issues with normality. Now these points here are doing a great job, but these points here and here give us the problem of normality, and thus it indicates that our data is not normal. But another way to check for normality is to use a histogram. A histogram of residuals can help us detect departure from normality. Now if the histogram follows a bell shape and is not skewed, the residuals can be said to be normally distributed. But before you plot your histogram, you have to install a package called MASS. Since I've already done that, I'm going to run these lines of code. And this gives us our histogram. And as you can see from our histogram, it has a long right tail, which means that the TIs are not normal and we cannot fit a redistribution here. That implies that our residuals are not normal. Now, since this assumption works on the same line as the homoscedasticity assumption, the rectification method here would be to use the same transformation that helps us stabilize the homoscedasticity assumption, and it is also helpful in approximately normalizing the error terms or the residuals here. Thus, it is best to check if the error variance transformation works and if the departure from normality still persists.